Alright, so for this video we are going to look at electronegativity and have time to discuss what electronegativity is. Now, by definition, electronegativity, this is the ability of an atom to attract bonding pairs of electrons. So this happens only when there is a chemical bond. So that's why we say bonding pairs. When there is a chemical bond. So really, on the periodic table, the electronegativities are given for different elements. Now, if you see part of the periodic table that I have given here, you can see some trends of electronegativity. So the electronegativity increases as we move from this side to this side. So this side has higher electronegativity. This side has low electronegativity. Now, also if you check, you will see that electronegativity increases as we go up. So this part has low electronegativity, this part has high electronegativity. So in terms of the trends of electronegativity look like this. So it increases as we go this side and increases as we go up. So it gives us this type of, or this kind of an arrow, where you see as we go this way, we see an increase in electronegativity. As we go up, we see an increase in electronegativity. So really, electronegativity explains bonds that we call polar bonds. But before we go there, let me just show you something. If you look at fluorine here, fluorine is the most electronegative atom. So most electronegative atom on the periodic table. So it is followed by oxygen. These two are the most electronegative, fluorine and oxygen. Then we have chlorine here and nitrogen. So if we look at the really the atoms that are really electronegative on the periodic table, it is these atoms: nitrogen, oxygen, fluorine, and chlorine. Bromine a little bit and iodine a little bit. You can see that the electronegativity of iodine is similar to the electronegativity of carbon. Now, some things that we need to understand. Normally when we form chemical bonds, we look at the differences in electronegativities. So when forming chemical bonds, we look at differences in electronegativities. So we will indicate if this is the difference in electronegativity, this is the type of chemical bond that is going to be formed. If this is the difference in electronegativity, this is the type of chemical bond that is going to be formed. So let me just give you an idea. So if the difference in electronegativity between two bonding atoms is 0.5 or is less than, so let me put less than, so is less than 0.5, the bond that is formed is a pure covalent bond. is a polar covalent bond. So you can see that 1, this is between 0.5 and 1.6. Therefore, we are going to comfortably say the bond FCl is polar because it has an electronegativity of 1. So because it has an electronegativity of 1. So that's how you determine a polar bond. Let's look at another example. Is the bond Cl or polar or non-polar? So what we are going to do is the same thing. We'll put this one here, Cl, and then put this one here, O. Right? So what do? We go here, oxygen. What is the polarity of oxygen, or the electronegativity of oxygen? It is 3.5. The electronegativity of chlorine is 3.0. So then you come here and say, all right, the change in electronegativity, you start with the big number, is 3.5 minus 3.0, which is 0.5. But we say that if change in electronegativity, that is N, is less than 0.5, the bond is covalent. But as you can see, this one is equal to 0.5. So because it is equal to 0.5, it is more than this less than 0.5, right? If it is equal to 0.5, we know that between 0.5 to 1.6, the bond is polar covalent. Therefore, the bond ClO is polar covalent. So really, you need to know especially electronegativities of these. They are very important. That's what you're going to face mostly. And even just understanding that as we go this way, electronegativity increases. As we go up, electronegativity also increases. And for you to determine whether a bond is polar or non-polar, you need to subtract the two electronegativities, starting with the bigger one and then the smaller one. So let's look at another example. So we just need to make sure that you got different examples. Is the bond CH polar or non-polar? So we go back here, look at CH. C has electronegativity of what? 2.5. So we are going to put 2.5 here. H has electronegativity of 2.1. So the change in electronegativity is 2.5 minus 2.1, which is 0.4. Right. But we know that for anything less than 0.5, the molecule is non-polar. So this bond here, the bond CH is pure covalent. It's just a normal covalent bond because its change in electronegativity is less than 0.5. So that's how you determine that this molecule, this bond, especially this chemical bond, is polar, this chemical bond is non-polar, by using electronegativities. Now let's look at another problem. Is the bond MgO polar, non-polar, or ionic? So if you want to use this formula, you go to here, Mg and O. O has electronegativity of 3.5. Mg has electronegativity of 1.2. So the change in electronegativity is 3.5 minus 1.2, which is equal to 2.3. But we know that change in electronegativity of greater than 2, we have an ionic bond. Therefore, the bond between MgO is ionic. Now, what about if we have another molecule? So is the bond between aluminum and which one should I take? N. Aluminum and N. Ionic or polar? So we put these ones together, aluminum, N. So we come to aluminum. The polarity of aluminum is 1 point. The electronegativity of aluminum is 1.5. The electronegativity of nitrogen is 3.0. So always we start with the bigger one. Change in electronegativity is equal to 3.0 minus 1.5, which is 1.5. So we know that between 0.5 to 1.6, it is polar covalent. So if we use that, we can comfortably say aluminum nitride is a polar covalent. But the issue is, this works well when we have nonmetals only. Right? So this works well when we have non-metals only. So in this case, aluminum is a metal, nitrogen is a non-metal, And also 1.5 is close to 1.6, which means this one is an ionic bond with some polar covalent characteristics, right? It's ionic bond because it's a metal and a non-metal, but because it is within these, it has some polar covalent characteristics, although it is an ionic bond. So that's how you determine whether a chemical bond is polar, whether a chemical bond is non-polar. So that is one way. Now another situation is, how do you determine if a molecule is polar or non-polar? Not just a chemical bond. How do you determine if a molecule is polar or non-polar? So we are going to put molecules here. So is H2O polar? That's a question that we need to address. So for you to determine if a molecule is polar, the first thing is determine what its Lewis diagram and shape is. So write Lewis diagram and shape of the molecule. But first, you need to determine that the chemical bonds themselves are polar. So you can come here and say oxygen and hydrogen. Oxygen is 3.0 or 3.5. Hydrogen is 2.1. If you subtract them, they give you 1.4. And 1.4 is between 0.5 and 1.6, which means it is within the polarity range. So the chemical bond itself, OH, is polar. But we are talking about the whole atom. Is the whole atom polar? So the first thing you do is determine if the chemical bonds in that atom are polar first, and then write a Lewis diagram of it. So not to take much time, for water, the Lewis diagram and shape is this one. Right? So this shape, the geometry of this one is tetrahedral. The shape is bent. So because it is bent, this molecule, what happens is it has polarity. But how do we show that? Let's suppose I write this molecule here, or I write this chemical bond, O and H. This part, the O, is more electronegative than the H, which means this one will be partially negative, right? And this one will be partially positive. This shows that the electrons will be close. The bonding electrons, the electrons connecting the oxygen and hydrogen will be close to the oxygen. So in that case, you show an arrow showing electrons are going towards this side, and then put something like that. So you need to indicate that electrons are moving from hydrogen towards the oxygen, or the electrons will be close to oxygen. So what I'm doing here, I'm drawing an arrow to indicate the electrons going towards oxygen here. Also here, indicate the electrons going towards oxygen. So if I add these two arrows, they will indicate that the total motion of the electrons will be towards oxygen. So just having this type of motion tells me that if I add this one and this one, it gives me this polarity here. So we'll say that this molecule is polar because oxygen and hydrogen are polar. Oxygen and hydrogen are also polar. And the molecule itself, because the molecule is bent and not symmetrical. So this is important. A polar molecule must have polar bonds and also must not be symmetrical. These are the two statements that you need to determine to make sure that your molecule is not symmetrical, but it also must have those polar bonds. If it does not have polar bonds, then it is a non-polar molecule. If it has polar bonds, it may be a polar molecule, but for it to be a polar molecule, it must not be symmetrical. What do I mean when I say symmetrical? Symmetrical means the polarities of individual bonds in the molecule must not cancel to zero. Now, if they cancel to zero, then the molecule will have a zero polarity, and it will be non-polar. So, like here, if we look at this one, right? This one, this individual bond is polar, and this other individual bond is polar. So if you add them, they don't need to give you a zero answer. If they give you a zero answer, then the polarities have cancelled. Right? If they give you a positive answer, then the molecule is polar. And because this one is bent like this, they cannot cancel. If it were straight like this, then they would have cancelled. And you see what I mean by that. Let's look at this molecule. Let's look at carbon dioxide. Is carbon dioxide polar or non-polar? Right? So for this one, first you need to check the polarities of the bonds. C and O. That's the first thing. Check the polarity of individual bonds there. So C is 2.1 or 2.5. O is 3.5. The difference is 1. So N is equal to 1. Which means this bond is polar. The CO bond is polar. So we can proceed from there.
So you said non-polar apart from
Yeah, just.
growth
So after that, we need to determine the Lewis diagram of carbon dioxide. So the Lewis diagram of carbon dioxide is COO. So if you look at this, the arrow, if you have carbon and oxygen, the arrow moves from, because this part is partial, positive. This part is partial, negative. So the arrow will move this way. From the positive to the negative. So we can say we have this arrow here moving this way from the positive to negative. But also if we add this one, another arrow will move this way from the positive to negative. Mm-hmm.
How do you know this part is going this way?
Yeah, because the one with higher electronegative is negative in the molecule. Right. So this one has higher electronegative, so the electrons need to go that side. This one has higher electronegative, the electrons need to go this side. But as you can see, this electronegativity and this electronegativity, are they different or equal? Between here and here and here and here. They are equal, right? They are equal and in a straight line. So the the two electronegativities, electronegativities of C and O are equal, right? Opposite and in a straight line. That tells you that this molecule is symmetrical. So this implies the molecule is symmetrical, and thus the polarities cancel each other. So the polarities cancel each other, which means CO2 is a non-polar molecule. But although it is a non-polar molecule, it has two polar bonds. So although it has two polar bonds, but we know that the two polar bonds have cancelled each other. So because of that, the whole molecule is non-polar. That's what we mean when we say if a molecule is symmetrical, that molecule is non-polar. And symmetrical means that the one side is exactly the same as the other side. So they cancel each other. So let me stop this one here.